So the next talk will be given precisely by Thomas Dubos, who is a professor at École Polytechnique and researcher at the Laboratoire de météorologie dynamique.
Okay, yes, it's on the left. Thank you. Thank you. Okay. So let me thank the organizers for putting together this interesting set of speakers. So my understanding is that my role here is more to present the pre-AI perspective based on equations and physical principles. And so what I will do, I think it will last around 50 minutes maybe, and there will be time for questions at the end. So I present actually only a certain branch of approaching this problem of formulating and solving numerically the physical part of the models. And to maybe put that into perspective, let me first mention that at the biggest level, we are talking about comprehensive Earth system models, which have different components to represent, say, the atmosphere, the continents, vegetation, optionally chemistry, the ocean, sea ice, optionally marine biochemistry, and the atmosphere. So we have already subcomponents in these system models, but even at the level of, say, the atmosphere or the ocean, there is this traditional distinction between, say, the resolved part, so that was the so-called elegant part in the previous talk, and the unresolved part, the so-called messy part. And this is a very classical distinction in all these models, to have like the so-called dynamics based on solving, say, Euler equations, and then the physics, which add a statistical representation of the effect of the unresolved processes, the processes that are too small to either to be representable on a grid, or they are also too small to be reasonable to represent. It can also be a decision to decide that the model, the model's role ends below a certain resolution, because that's what we are interested in, is the coarser part of the reality. So for a typical ocean model, you have several approximations I will come back to later. And so this is where I will spend most of my talk, on that, say, comfort zone where we have physical principles and nice equations. But I try to make it in a way that at the end I can connect somewhat to the more difficult part, which is representing these subgrid processes. And this is where, as we have already seen, machine learning has made very impressive steps recently. And I'm showing this graphic, which is from the ClimSim dataset, which is a dataset proposing inputs and outputs as a challenge for machine learning scientists who would like to provide emulators. And interestingly, as input, so what they do is they provide, they define this basic learning problem as, okay, I give you, for every point on the planet, a column of, say, specific humidity, temperature. Maybe I should use this, right? Specific temperature, specific humidity, but all presented as independent columns. And then your job is to predict, say, the tendency of moisture or the net surface shortwave flux or the rate of rain, but all on independent columns, which is the dominant paradigm in the coarse resolution GCMs in the way they represent these subgrid processes. So in practice, I will provide a super quick introduction to Hamiltonian geophysical fluid dynamics, which is the branch where I have some insights, and provide two applications of this formalism. One which is to numerics, which has, I'm trying. It's a bit too low. Okay, yeah, maybe it's better. Which has seen a lot of progress in the last 10 years. I show also how it can be used to better understand the approximations that are made in the models. And finally, I will try to discuss to which extent formalism can also help in this more messy domain. Okay, so what are we talking about? So Hamiltonian geophysical fluid dynamics, it's a branch of geophysical fluid dynamics that tries to formulate the models that describe the flow of the atmosphere or the ocean, either as a least action principle or as a Poisson bracket Hamiltonian formulation. So why would we want to do that? So the least action principle, it is well known that if you have some symmetries in the system, then there's a theorem by Noether that tells you that there are conservation laws. So it's a very powerful way to build systems with conservation laws, which of course is important in physics, such as energy and others. And the Poisson bracket dynamics, it's like two faces of the same coin. And so it looks like this. It's a different point of view where you, instead of writing individual equations for each quantity in your model, you write a kind of master equation for any quantity that you can compute for the model. So it contains, in this master equation, contains all the information on the evolution of anything in the model. And for Hamiltonian systems, it turned out that it can be written as a bracket with certain properties, among which the existence of so-called Casimir invariance, I'll show that a bit later, which can lead to methods that are able to study the stability of the system. So this is a theory that is very well understood mathematically, with tools that personally are beyond my expertise, but tools from differential geometry and Lie groups. And there are well-known review papers by Morrison and Holm and co-authors, and maybe more recent ones. It's also very general. It can apply to magnetohydrodynamics, complex fluids, and other domains. I'm trying to not run out of time. Okay, so how does it work? Basically, what we have, we have some transported fields, right? We have some advection equations, like this could be a mass budget, like this one. So rho is a mass per unit volume, u is the fluid velocity, or this could be like a concentration of say water vapor or salinity. But from the different geometry point of view, there are both different variants of a Lie transport equation, like this one, with rho a density and q a scalar, so they have a slightly different Lie derivative. And then the crux of the variational principle is to derive all the variations of these transported fields from a single Lagrangian displacement field, and also the velocity variation will derive from this single Lagrangian displacement field. So this allows to make all the variational calculus entirely in the Eulerian frame. You don't have to adopt a Lagrangian point of view and then go back to the Eulerian picture. And then it's just a matter of say, computation and that I am able to do. So you don't need to know differential geometry to do it. And to formulate your least action principle, basically, typically your action is an integral. I will show an example in the next slide. And then after some manipulations, you obtain the momentum balance. So I show that for shallow water system. So the shallow water system, it's like an archetype of geophysical fluid dynamics model. It's a single layer system where you have, say, horizontal velocity u, and you have a layer thickness, say h, which is with the pressure being proportional to the layer thickness. So you can write a mass budget with pressure playing the role of mass. So pressure here will be a transported field obeying the transport equation of rho in the previous slide. So the way to obtain the shallow water system is to build the Lagrangian in a classical way. So you have a kinetic term, so this is Lagrangian per unit mass. You have a gyroscopic term which will generate the Coriolis force. And you have a potential energy term which is proportional to thickness. So then you just inject all the bits of the machinery into your action and its variation, and you obtain the standard equation of motion for the shallow water system. So the beauty of this is that, for instance, you get naturally the conservation of potential vorticity, which is an important conservation law in the shallow water system and other geophysical systems, just because of the general form of the least action principle. It doesn't depend on the internal details of the Lagrangian. So I could change the expression of this Lagrangian, I will still get a conservation law for a different potential vorticity. So now this is how it works, and basically you will get more complex systems by adding more transported fields and having a more complicated expression of the Lagrangian. Now, if we want to have a Poisson bracket expression, we need to start from energy, and energy per unit mass. The procedure is standard. So you make a Legendre transform of the Lagrangian, which yields the energy in the usual form. So you have a kinetic part. So V is the conjugate momentum. And in this case, because of the gyroscopic term, V is velocity plus the planetary velocity r. So you have to subtract it and square to obtain kinetic energy. And then now you have plus potential energy. So the energy is the more intuitive quantity for physicists, at least. So when you integrate it with mass weighting, you obtain the Hamiltonian. And then that's where you take the Hamiltonian point of view. You ask for any quantity f, how it evolves with time. And this is just a matter of the chain rule. Then you can inject the equations of motions from the previous slide. And after some manipulation, you obtain an expression like this, because you realize that in the equations of motion, maybe I can show that. For instance, you have this gradient of B, where B has some expression as a function of the Lagrangian, but B has also a simple relationship to the Hamiltonian. So you inject this knowledge, and you obtain this kind of expression, which has the fundamental property of being antisymmetric into F and H. So this antisymmetry leads to the conservation of energy when the Hamiltonian is time independent, which is one of the main reasons why it's considered. It has other properties, one which I don't write down, which is the so-called Jacobi identity, which has a deep connection with this Lie group structure that I mentioned. For physicists, another important property is the existence of Casimir invariants. So Casimir invariants are special functions f, such that the bracket vanishes irrespectively of the specific value of the Hamiltonian. So that means that all the systems, even with different energies, will have these invariants. So in this case, the conservation of potential vorticity translates into the existence of a certain family of Casimirs. So that was my super quick introduction. So the idea is that scientists have developed similar formulations for the three-dimensional fluid systems that are at the heart of the atmospheric and oceanic models. And now a first application of this nice and beautiful and elegant formulation is to have to design numerical schemes which inherit some of the properties of the continuous system. So these numerical schemes, for instance, they can be built on top of a mesh like this on the sphere, so-called the cube sphere. We've seen an example in the previous talk. Or more irregular meshes like this, where you have some triangles here, and we form the Voronoi dual of that mesh here. So what's the general idea? So the general idea is not so recent. It is to imitate that Poisson bracket structure at the discrete level, basically. And in fact, many energy-conserving schemes have been devised in the 70s and 80s, and in hindsight, you can show that they have implicitly this structure. So the idea was put forward 30 years ago or so, but it gained traction mostly in the last 10 or 12 years in various models and with respect to various numerical techniques, from finite volumes, finite differences, to finite elements. So I say quasi-Hamiltonian because you can't really keep everything Hamiltonian from the continuum to the discrete level. In fact, you lose almost all of the Hamiltonian properties. The first of which is the Jacobi identity, which means that the discrete system doesn't have a symplectic structure. Usually you lose most Casimir invariants. For instance, in the previous case I mentioned all these integrals with respect to potential vorticity. Usually if you keep two of them, like the total mass corresponds to f of q equals 1, and total entropy corresponding to the f of q equals q squared, you're very happy to have basically two invariants instead of a whole family. So what's left, that is relatively easy to transfer to the discrete setting, is antisymmetry. So how does that look like? I just try to provide a sense of how it works on that shallow water system and only on that part of the bracket. So for antisymmetry, you can decompose the full bracket into pieces and work independently on each piece to make sure that it's antisymmetric. So that's the part I focus on. And so say you have this kind of mesh. So that's from a paper by Sadoni in the 70s. And it's for various reasons, it can be advantageous to have, say, pressure. So that's my pi. And the velocity components at different places. So now, instead of having a function of the continuous fields, I will have a function of a finite number of samples of velocity at certain points and pressure at other points. And I'm asking, what I will do is I will write down a discrete bracket which is an imitation of this one. So I will discretize this divergence by a finite difference in the x direction. So I will take the difference between these two u's, and I will symbolically put it here. Same in the y direction. And I can do something similar for the gradients. So if I take the finite difference between these 2 points, it gives me a gradient at that point. So this is an imitation of the continuous antisymmetric bracket, and by design it's antisymmetric. But if I want to derive the equations of motion from the bracket, what I want is to rewrite this with all the derivatives of f without anything in front of them. So that's what I do here. And the key property that enables to move from that line to the next line is this discrete integration by parts property. So typically, having a discrete integration by parts property is essentially equivalent to the antisymmetric property of that part of the bracket. And that's what you try to get in your numerical schemes. So once you have this, you see that I could choose a specific f, which is just, say, that value of u at that point. And then all these derivatives, df, du, would be 0 except for 1 point and 1 value of u. So I will get the evolution of any quantity that I want. So it goes both ways. I can derive the bracket from the equations of motion, and I can derive the equations of motion from the bracket. So in this case, that's what you get. So your equations, your discrete model is fully specified after you have given an expression to the total energy. So there are, of course, different possible choices, but a natural one is this one, where the only complication is that because the pressure and velocity are not at the same point, you have to do some averaging. So this is really typical of the finite difference schemes from the 70s and 80s. For instance, to compute mass-weighted kinetic energy here, I will square u, and I will do an average of pressure between the two neighboring points. So after I compute my derivative of energy, I find that this is a centered mass flux, and this is the corresponding expression for the Bernoulli function. So the advantage of this procedure is that we move forward instead of backward, right? What people were doing in the 70s, they would first decide on these expressions, and maybe that one, and then they would derive the energy budget and go back and forth until they have an energy conserving scheme. Now you can just write the bracket, and if the bracket is antisymmetric, for any expression of total energy, you have an energy conserving scheme. So it's a much more systematic procedure. So once this was recognized, it has been applied to various contexts. So one is this kind of unstructured meshes, and you can also add some ideas from discrete differential geometry, where, for instance, you can decide that one way to represent the velocity field is to choose as discrete numbers the integral of the velocity along one of these triangle edges. And once you've done that, there is a natural discretization for the curl, which is just to add all the three circulations. And then by the circulation theorem, this is a first order approximation of the curl, which by design has the property that the curl of a gradient is 0. So you can add extra IDs to add extra properties to the whole scheme. So in a finite element setting, basically there is the equations of motion follow directly from the bracket as soon as you take for your function f basically a dot product with some test function. So you get immediately the weak form. So the problem is rather to choose your function spaces wisely. So people have explored various possibilities with spectral elements, mixed finite elements, and even so-called primal dual finite elements. So usually the game is to find maybe some elements for scalars, which will be used as stream functions. Then you can use, you have a gradient, a rotated gradient that gives you non-divergent velocity fields, and then you have a divergent operator that gives you mass fields, all with like some kind of commutation diagrams that give you nice mathematical properties. So this has been used on for instance, the Metofis latest version of the weather forecasting model is based on this, and also the American E3SM high-resolution model. So just to conclude on that part, so quasi-Hamiltonian schemes, there are just one way of thinking about these schemes. It's by far not the only one. And it's not a cure for everything. One should not exaggerate the advantages of using this procedure. They don't. Basically, you get conservation of energy, and that's it. And there are many other things that need to be taken care of separately, like making sure you have good discrete dispersion properties, that you don't have unbalanced degrees of freedom, especially on unstructured meshes, and that you have to take care of various numerical instabilities that are always ready to pop up. So that was my brief overview of how these ideas have penetrated the realm of numerical schemes. And now I would like to spend a little bit of time on the equations themselves, so before you even try to discretize them. And so what I'm showing here, it's a portrait of Leonhard Euler. So the Euler equations are the name for the inviscid, fully compressible fluid equations. On the right, it's Valentin Boussinesq, who he's a French scientist. He's known for two very different things. One is the Boussinesq approximation that I will discuss, and another one is also sometimes called the Boussinesq approximation, which is rather a closure, which is the idea that a turbulent flux is proportional to the gradient of the turbulent quantity under consideration, which is also a very important contribution. But here I talk about the first one. So the question is how you go safely from a fully compressible system to a system where you have some constraints, you add some constraints on the density, which present a number of advantages. So why does it make sense in the atmosphere and the ocean? The basic idea is that in the atmosphere and the ocean, the pressure field has a very large static part. You know that when you go to the mountain, you can deduce your altitude from the measurements of pressure. And that's because pressure, to a large extent, is always the same. So it makes sense to decompose it into that static part, which depends only on altitude z, and a time-dependent excess pressure, which is the important one. It is the one that will put the fluid into motion. Then you can derive a density profile by hydrostatic balance from that reference pressure profile. And when you inject that into the forces that act on a fluid parcel, basically this term will cancel this term. And you end up with, instead of having two large terms that are almost cancel each other, so that you don't really have a good feel or good sense of the source of motion, you end up with two small terms, each of which can drive motion. So this is the gradient of the excess pressure, and this is the so-called buoyancy. So buoyancy B, it's a relative difference of densities, so density of the fluid parcel and the density of the environment. So basically it answers the question, is my fluid parcel lighter or heavier than the reference environment? In the first case, it will feel a force upwards, and in the second case, it will feel a force downwards. Then it makes also sense to make approximations on that term, because rho, for instance, in the ocean varies only by less than 1%. So if you are happy with a 1% error on that term, you could just say that rho is a constant. But of course, you can't make rho constant for buoyancy, because otherwise you would lose that very important aspect that, for instance, if you have hot fluid, warm ocean water, then it tends to rise, and if you have cold ocean water, then it tends to sink. So you end up with an approximation which is different on this instance of rho and that instance of rho. And it's not obvious if you just do this based on, say, quantitative grounds, that you will end up with a model that conserves, for instance, energy. Right? It's very easy to tinker with the equations of motion and end up with a model that has lost its conservation properties. So how to avoid this? So the general principle, along the lines of what I've already introduced, was put forward by Salmon in the 80s and Holm in 2000s. and the Hamilton's principle asymptotics name was coined by Holm. The idea is very simple. Don't expand the equations of motion. Don't do that. What you should expand is the Lagrangian. So do your approximations directly in the Lagrangian. This guarantees that you will not break the structure of the model. So it's very easy in that case to preserve symmetries and to have the desired conservation laws. So for instance, in a fluid, total energy, so if I call E energy per unit mass, rho is still mass per unit volume, you will have one part which is kinetic, and the other part which is internal plus geopotential. Sorry, there's a missing O here. So internal energy, I can write it as enthalpy minus P over rho. So that's from standard thermodynamics. So the whole energy can be written as kinetic plus this sigma, which is called static energy, minus P over rho. And sigma for a fully compressible fluid will be enthalpy plus geopotential, which is the potential energy due to gravitation and the centrifugal force. So now, applying this idea of Hamilton's principle asymptotics just means that I can replace this compressible expression of sigma by an approximate expression based on that decomposition of pressure into the static part and the excess pressure part. And if I write down the equations of motion that derive from this action or Hamiltonian, what we find is that, so P here is an extra free variable, so I ask that the variations with respect to P also vanish, and that gives me the equation of state in blue. And in red, I will have the corresponding expression of buoyancy. So if I make any modifications here, it will simultaneously modify the equation of state and this red term in a way that is mutually consistent and conserves total energy. So one way to do it is to do a quasi-linearization with respect to this excess pressure. Of course, there is an error, so it's a less accurate model. But you end up with a model where density, instead of being time evolving, is constrained to a fixed value. So that's one less field to predict. And also you gain by suppressing acoustic waves, which are typically unimportant for geophysical problems. And they cause a stiffness in the equations of motion. So they unless you do something special in your time integration, they will lead to very small time steps due to the CFL condition, as was mentioned before. So that's the main justification to do that. And technically, there are a few things that you can deduce from the Lagrangian point of view. Pressure becomes a Lagrangian multiplier. There's a systematic, well-known way to obtain the elliptic problem for pressure. And there is a simpler model where you have the reference profile linear in height, which corresponds to what ocean models do. In fact, what the model you get with this linear pressure is not exactly what ocean models do. It looks very much like what they do, with a very small difference. So here, when you crank up the computations, you end up with a buoyancy which is proportional to the difference between the specific volume computed at, say, the potential temperature and salinity of the water, minus the reference specific volume. So B is proportional to a difference of specific volumes, while in the standard Boussinesq approximation, B is proportional to a difference in densities, which is the inverse of the specific volume. So in terms of accuracy, it's the same thing. You make the same amount of error. But in terms of energetics, it's quite different, because for this model, people have spent a lot of effort in the last few decades to decide whether their Boussinesq models were energy conserving or not. And they finally managed to find a total energy that is conserved, but it's not possible to make a link between that energy and that of the fully compressible model, while it's straightforward for this equivalently accurate formulation. So if I summarize, so that's just an example. There are other approximations that can be treated by this approach, especially geometric approximations, like the shallow atmosphere approximation, approximations with respect to the Coriolis force, and also the hydrostatic approximation. So if you do that, you end up with a taxonomy of geophysical models, where because the approximations are characterized by how they modify the Lagrangian, they have a much more concise description than by, okay, there is this term in the equation that I change, and this other term in this other equation, and so on. It can clarify sometimes a confusion. So as I explained, my take on this is that buoyancy should be regarded as a proxy for volume and not mass. You can relax restrictions. All these models, they have been derived in the past by a more manual procedure, and sometimes the hypotheses that were used are unnecessary. So for instance, you can have an elastic model for arbitrary thermodynamics, including, say, moist air. You can have an arbitrary reference profile, and so on. And this is also because you can compose approximations, so you can decide, okay, I will do that approximation for the geometry, and I will do the inelastic approximation on the other hand, and the hydrostatic approximation on the other hand, and they can all be combined together. For the rest of the talk, so I have 20 minutes left, that's very good. The important thing here is that this approach connects the energy of various models. So that means that after the fact, we can add terms that are beyond the reach of these variational principles, which are all the terms that describe irreversible processes. So, for instance, viscosity, conduction, and diffusion. So if you want to add these terms in a way that's consistent with the first and second law, it's very important that, say in a Boussinesq model, it's very important that the Boussinesq energy is an approximation of the fully compressible energy, because that means also that you have a well-defined notion of temperature in your model, which is an approximation of the fully compressible temperature. And so you are able to respect properties like conductive heat flux goes from warm to cool, that are consistent with the second law. And of course, all these models will share the common Hamiltonian structure, which can be exploited for numerics, as I've explained before. But for the rest of my talk, the important point is this one. After the fact, we can add these terms, and so we can start very prudently to add irreversible terms in addition to the reversible part of the model. So here I claim that the problem of dynamics is mostly solved. So it's mostly solved in that sense, right? That we can do all these things using this variational approach. Does that mean that there is nothing left to do? Of course not. So I think what's left to do is clearer if we write this hierarchy. So what we are interested in is at the very top here, right? It's a general circulation model that has decided to represent only the atmosphere at a relatively coarse scale, say 100 kilometers. So that means that to arrive at that model, we have made at least one or maybe two steps of coarse graining. So where we are safe is at the lower part of the hierarchy. What we know how to do well now is how to go from the compressible Navier-Stokes. We can add some soundproof approximations like the Boussinesq approximation I described. And we can add on top of that the irreversible terms. We can make other approximations with respect to like the planetary rotation and things like this. And that takes us only to, say, direct numerical simulations, which are very detailed simulation at the millimeter scale on very first principles. What we would like to do is to do this coarse graining and at least reach the stage of so-called large eddy simulations, which are simulations that capture only the scale of a few tens of meters, for instance. And every time you do a coarse graining, then you have extra terms in your equations that you cannot really determine from first principles. So you need closures. So that's a different thing, right? It's not like you do asymptotics and you have a small epsilon and you do approximations. It's not an approximation, it's a closure. So it's a closure where some extra term in the equations has to be empirically related to the known terms. So the Boussinesq closure is one of them, for instance. You need here a heat flux or say a composition flux, like a water flux in the moist atmosphere. And say, okay, that flux, I think turbulence mixes things up, so it has to go from the places where there's a lot of water to the places where which are dry. So all these closures, they tell a story. They are not just machines that relate inputs to outputs. They are based on a story and on characters. Okay, and then there is another coarse graining where you have other closures, say for convection or even worse convection, moist convection. So that's where all this messiness comes in. So can theory help? I think if you interview people which are not of my kind, who actually create parameterizations, they would probably answer you that so far theory has been of very little help to them. What is of help to them is mostly data, physical intuition, and try and error. So can we do better? So I will try to show that there are maybe some modest ways forward to provide some insight into building these closures. So one possible avenue is to identify less obvious invariance properties. And so I will mention one of my recent works on this. So for instance, if you look at your fluid equations, being fluid, they rely on thermodynamics, right? You have somewhere an equation of state, so underlying the equation of state, you have a Gibbs function or an enthalpy that generates them. So if you give me a Gibbs function, I know all I need to know about the thermodynamics. Any thermodynamic function can be deduced from the Gibbs function or from specific enthalpy. For instance, specific volume. But if you look at the models themselves, they are insensitive to certain changes in these potentials. So, for instance, the Euler model is invariant with respect to a relatively wide class of transformations. That's actually a Casimir invariant here. The Navier-Stokes equation, which has more terms, is less invariant, but it's still a little bit invariant. You can add a constant to the so-called reference enthalpies and entropies. And so if you write down a closure, it's not obvious that it will always have this invariance, while it should, right? Because when you do the averaging, if your Navier-Stokes model has this invariance, the average model will also have it. So closures should always inherit these invariance properties, and that requires some care. It's possible, but it requires some care. And I haven't finished that, but I think starting from this, you can actually show that the down gradient closures in the style of Boussinesq can be actually shown to be consistent with invariance and the first and second laws. And so that was more or less turbulence and invariance. Well, that was more the question on invariance and exemplified with turbulence. Now, I've mentioned in the abstract that I would challenge the idea that the tendencies basically can obey just an ordinary, not ordinary, usual partial differential equation. So I would like to specify what I mean on that example of dry convection. Dry convection, what is this? If the lower atmosphere is warm, then warm air will rise and will create mixing, right? But that's also a way for the atmosphere to lose energy to space, right? To higher altitudes and ultimately to space. So that's one of the mechanisms that will cool down the surface. And there is a well-known criterion called static stability criterion that tells you when this triggers. So in ancient climate models, they had this way of doing. You would compute the time derivatives due to dynamics and then say to other processes like radiation. And maybe radiation or maybe dynamics, they would warm up the lower layers too much. So that would violate that criterion. So what you would do is to look at the column and then basically move heat upwards until the criterion is verified again. If you try to write this as an evolution equation, what you get is something like this. So this will have an explicit expression, right? Like something like minus u grad t plus other terms. So it's computable from the present state of the fluid. And this too, right? It's more complicated. You have to take into account millions of absorption lines, but it's doable. But this term is the energy flux, the upward energy flux due to convection, and its divergence will warm or cool the column. And this flux doesn't have an explicit expression. It just says, okay, this flux is positive everywhere where it's necessary, which means everywhere that you are at the boundary of stability. So I've talked about that with Colin Cotter from Imperial, and he says that it's called variational inequality. Okay, so my belief is that this is pervasive because you have fast physics tendencies which correspond to adjustment processes. So that's one adjustment process, but you also have adjustment processes when you have too much water vapor, and then suddenly you must create a cloud, and almost instantaneously this cloud will cause rain. So I believe this kind of structure is everywhere in the models. So just to conclude, I'll come back to that initial picture. So in this ClimSim data set, they just looked at what's written in the papers, and in the papers that's what is written. The physics package will take the column, each column independently. It will look at the temperature, moisture, wind, and the surface condition, and for each column independently, it will compute the derivatives, the time derivative, how it changes with time. But the column it takes has actually been modified by the dynamics already, and in practice, what the physics do is they do time integration themselves. So I think that this is a bit, probably this is, we have unwillingly told a small lie to our machine learning colleagues that, in fact, this information is probably insufficient to predict these outputs. So that's what I would take from my second very small example. And from the first example, what I would take is that I'm not sure, of course, if you want to predict the tendencies of all processes at the same time in just one shot, probably you don't have any choice but to just put everything in the basket, right? Wind, temperature, moisture, pressure, whatever you have. But that's never going to tell you any kind of story of how you get from here to there. If you look at more individual processes, then maybe there is some value to think a second time on the inputs and make sure that the inputs you give obey these invariance properties, that at least those that you're aware of, and also that you don't give information that's not needed. Like, I mean, for radiative transfer, you don't need to provide wind. We know that it's useless. And for different processes, we have a priori knowledge of what is useful in terms of inputs, and also what's good in terms of outputs. For instance, I see here that we have some fluxes, right? So if the outputs are energy fluxes, then we can ensure that the model has some notion of conservation of energy. If the outputs are directly temperature tendencies, then anything is possible. Okay, so that's my concluding slide. And so to summarize, I think there have been very nice advances recently, especially in the last 2 decades, on the side of dynamics, both on the models themselves and in the numerics. And maybe in the future, people like me doing more theoretical work can also find ways to help in the design of both physics-based and also data-driven parameterizations.